Module 5, Lecture B, Capstone Tool Design. By the end of this lecture, you will be able to design a command line engineering tool with clear inputs, calculations, outputs, and error behavior. Integrate functions, collections, file handling, and formatted reports into one coherent script, and evaluate the final tool for correctness, readability, and usefulness in an electrical engineering workflow. Project planning, tool requirements. When defining requirements for a command line tool, start with the user's needs rather than programming details. In electrical engineering, this means identifying the specific task the tool supports, such as estimating voltage drop or producing lab data reports, and setting clear limits so the project does not expand beyond its purpose. Good planning clarifies the problem, the intended users, and the level of detail appropriate for command line use. When designing a command line engineering tool, first define how users will interact with it and what information they must provide. The tool should make its required data, assumptions, units, and outputs clear, whether users enter data directly, provide files, or use both methods. Its behavior should be predictable and simple, guiding users toward accurate results without unnecessary complexity. When designing a command line tool, define the expected outputs and error handling early so the tool is reliable and easy to test. Results should be presented clearly, from quick summaries to detailed reports, to support review and decisions. Errors should give helpful guidance when users enter invalid data, which is especially important in electrical engineering, where mistakes can affect equipment choices and safety. Python code. Tool requirements. This script introduces early tool requirements using a voltage drop example. It shows how requirements define the needed inputs, expected outputs, and possible errors. The script uses the path class from the pathlib module to work with file paths in a cross-platform way. Here it helps create and manage the path for writing the voltage drop report to a text file, making the file handling more reliable across different operating systems. A requirements dictionary defines the tool's key behavior. It estimates voltage drop for a single-phase feeder, reads input from a file using safe defaults, and presents both a screen summary and a detailed text report. It also specifies that invalid engineering values should be explained clearly, helping the tool run consistently and give useful feedback. A sample input dictionary is defined for a voltage drop calculation. It provides the needed electrical values: 240 volts, 28 amperes, an 85-foot conductor length, and a resistance of 1.24 ohms per 1,000 feet. These preset inputs let a command line style program run the calculation consistently. The function first identifies the essential fields a job record must contain. It checks whether any of those fields are missing, and if so, returns false with a message naming them. This validation makes sure the required data is available before any calculations begin. The function gathers the required numeric electrical inputs from the job data and checks that each one is positive. If any value is 0 or negative, it returns false with a message explaining that all electrical inputs must be positive. This validation prevents invalid values from being used in later calculations. The function returns a success status and a message. A true result means the input values passed the basic engineering checks, and the message confirms that validation succeeded. This indicates the data is ready for further processing with no detected issues. The function estimates voltage drop from a conductor's resistance. It uses twice the cable length to represent the full current path, finds the total resistance from the resistance per 1,000 feet, then multiplies by the current to get the voltage drop. It also reports the drop as a percentage of the starting voltage. The function creates a voltage drop report by first checking whether the percentage drop is within the 3% limit. If it is, the result passes. Otherwise, it is marked for review. The report then summarizes the requirement purpose, the input values for voltage, current, and length, the calculated voltage drop in percentage, and a final decision based on the planning limit. It returns these lines as one complete text report. Before any calculations begin, the code checks whether the input data is valid by using the job validation function on the sample job data. The function reports whether validation succeeded and provides a short message with the result. This helps ensure later calculations use complete and correct data, reducing the chance of errors. The code first validates the input data and stops with an error message if the requirements are not met. If the data is valid, it calculates the voltage drop and percentage drop, then creates a report with the inputs, results, and whether the outcome is acceptable. The report is saved to a text file and also printed to the screen, along with a confirmation of where it was stored. This script checks whether a single-phase feeder meets a voltage drop requirement. It first validates that the required inputs are present and positive, then calculates the drop using loop length and conductor resistance. The result is reported as both volts and a percentage of the starting voltage, with drops of 3% or less marked as pass and larger drops sent for review. A summary report is printed and saved, while invalid inputs produce an error instead of running the calculation. Functional requirements. Functional requirements define exactly what a command line engineering tool must do when it runs. They turn a broad idea into concrete operations such as calculations, decisions, file handling, checks against limits, and clear output. In electrical engineering tools, this might include sizing conductors, checking voltage drop, computing current levels, comparing ratings, and flagging unsafe results. The purpose is to replace vague goals with precise tasks that can be implemented and tested. A strong functional requirement should focus on the user while giving developers enough detail to build the feature correctly. It should state what the tool does, under what conditions, and what result is expected. Clear requirements, such as defining the exact calculations or report outputs, reduce confusion and separate essential features from optional improvements for later versions. Functional requirements should define not only what a tool calculates, but how it responds to changing conditions and interprets results. Many engineering tools need to guide decisions, such as checking whether a suggested value is valid or warning users about unrealistic inputs. Planning these decision points before coding helps shape clear outputs and makes validation easier through targeted test cases. Python code, functional requirements. Before building engineering tools, first define the functional requirements so each one can be tested as specific tool behavior. In this example, the focus is on safely loading transformers. The example defines a dictionary of simulated command line inputs for a transformer loading tool. It provides the transformer rating as 75 kilovolt amperes, the secondary voltage as 480 volts, and the measured current as 82 amperes. These values give the tool realistic data for calculating transformer loading. A configuration is set up to define transformer loading limits and reporting. It triggers a warning when load reaches 80%, marks overload at 100%, and saves the report in a specified text file. This keeps the loading criteria clear and the results documented. This function estimates transformer percent loading by first calculating apparent power in kilovolt amperes from the voltage, current, and square root of 3, then converting the result from volt amperes. It then divides that apparent power by the transformer's kVA rating and multiplies by 100 to get the load percentage. The function returns both the apparent power and the percent load. This transformer loading function classifies percent load using warning and overload thresholds. If the load meets or exceeds the overload threshold, it reports an overload and suggests reducing demand or using a larger transformer. If it is below overload but still meets the warning threshold, it reports high loading. Otherwise, it indicates the transformer is operating within planned limits, supporting safer operating decisions. The function first verifies that all required inputs are present in the input dictionary. If any are missing, it raises an error explaining that required values are absent. Then it checks that all numeric inputs are positive, raising another error if any value is 0 or negative. Together, these checks ensure the inputs are complete and valid before calculations begin. The function calculates transformer loading from the rating, secondary voltage, and measured current, then determines the percent load. It uses the loading classification function to decide whether the transformer is operating normally, nearing a warning limit, or overloaded. Finally, it returns a short engineering report with the key inputs, calculated load values, and the resulting status decision. The process first validates the inputs to make sure required values are present and positive. If validation succeeds, it builds a transformer loading report, formats it as text, and saves it to the specified output file. If validation fails, the error is caught, and the report text is replaced with a safe stopping message, allowing the tool to handle problems gracefully. The code displays a report summarizing the transformer loading results, including the calculated load and its classification. It then confirms that the report was saved by showing the file name, so the user knows the output is both visible and stored for later use. This script estimates transformer loading from the transformer rating, secondary voltage, and measured current. It checks that the inputs are valid, then calculates apparent power and percent load. Based on set limits, it labels the condition as OK, warning, or overload. Finally, it prints a summary, saves a report, and stops safely with an error message if the inputs are invalid. Input requirements. Input requirements for a command line tool should be defined as carefully as the calculations it performs. Each required input should have clear units, valid ranges, and mandatory status so the tool can work reliably. This reduces confusion, prevents input errors, and lets users focus on the engineering task. Choose an input method based on the tool's purpose, the user's experience, and how often the task will be repeated. Interactive prompts are easier for beginners and simple tasks, while command line arguments work better for repeated or automated use. File-based input is best for larger projects, as long as the format and data stay consistent. Engineering tools should be designed to handle input errors without confusing users. They need to reject clearly invalid data, such as negative resistance or non-numeric voltage, while still allowing unusual but valid cases. Clear rules for acceptable inputs, defaults, and error messages build trust and let users focus on the engineering work instead of fixing avoidable input problems. Python code. Input requirements. Before starting calculations, define the required inputs, check that engineering values are valid, and provide clear errors or warnings when problems are found. We create a dictionary of raw inputs to mimic values coming from the command line or a configuration file. Each entry pairs a parameter name with a text value, such as voltage or current. Keeping these values as strings reflects how external inputs are usually received and makes them easy to access and validate later. The code simulates command line inputs for a voltage drop calculation. It uses a wire length of 250 feet, copper as the wire material, and a single-phase electrical system, which together determine the resistance and voltage drop multiplier. A resistance table stores the electrical resistance values for different materials, such as copper at 0.00124 and aluminum at 0.00204. This lets the program quickly find the correct resistance for a material, which is needed for later voltage drop calculations. The function gets a text value from the input data using a specified key, then converts that value into a floating point number. This makes the value usable for numerical calculations. If the conversion succeeds, the function returns the numeric result for further processing. The code validates that the number is positive. If the value is 0 or negative, it raises a value error to reject it. Otherwise, it returns the number for further use. The read choice function validates categorical input by retrieving a value, cleaning extra white space, and converting it to lowercase for consistency. It then checks whether the result is one of the allowed options. If not, it raises a clear error, naming the input and the accepted choices, helping prevent invalid values from being used later. The function checks whether the user's choice is allowed. If it is not, it raises an error that lists the valid options in alphabetical order. If the choice is valid, the function returns it. The function reads the voltage and current inputs and validates each one as a positive number using the appropriate units: volts for voltage and amps for current. This ensures the data is reliable before any voltage drop calculations are performed. The code first reads the cable length and confirms it is a positive decimal value, since this is needed for accurate calculations. It then validates the material type against the allowed resistance data, such as copper or aluminum. Finally, it checks whether the phase type is single-phase or three-phase, so the correct voltage drop multiplier can be used. The calculation adjusts for the electrical phase by using a multiplier of 2 for single-phase or 1.732 for three-phase. It then looks up the conductor material's resistance per unit length and uses it with the current and conductor length to find the total voltage drop. The code calculates voltage drop as a percentage of the original voltage, then checks whether it is 3% or less. If the drop is within that limit, it reports the status as OK. Otherwise, it gives a warning. The function returns the key inputs along with the calculated percentage and status, providing a concise voltage drop report. The voltage drop report function is run with predefined inputs to check and calculate the voltage drop. It returns the key results, including voltage, current, cable length, material, drop percentage, and a warning that indicates whether the drop is within acceptable limits. The code demonstrates the input values needed for a voltage drop calculation. It displays the voltage, current, cable length, and material type in clear formatted output, so the user can understand the electrical conditions and physical setup being used. The code reports the voltage drop as a percentage of the source voltage, rounded to 2 decimal places, so the user can see how much voltage is lost in the cable. It then shows an engineering status of OK or warning based on whether the drop is within the allowed limit. If inputs are invalid or missing, the code catches the problem and prints an error message. This script estimates voltage drop in an electrical circuit from predefined inputs. It checks that numeric values are positive and that choices such as material and phase are valid, then calculates the drop based on material resistance and circuit type. The result is shown as a percentage of the source voltage, with a warning if it exceeds 3% and an OK status otherwise. Invalid inputs produce a clear error message. Integrated script workflow. Reusable script components. Reusable script components help turn a basic command line tool into a maintainable electrical engineering workflow. By separating tasks such as reading data, checking inputs, running calculations, and creating reports into focused functions, the script becomes easier to test, update, and understand. This modular structure makes the program work more like a well-organized engineering system, with each part serving a clear purpose. Reusable engineering components should be designed to work with collections, since real project data often contains many related values rather than a single item. By accepting data in a predictable structure and returning usable results, a component can handle inputs from different sources without changing its core logic. This makes the same component easier to reuse across multiple projects. When scripts work with files and reports, reusable components keep the process clear and maintainable. Separate data loading and error checking from report formatting, instead of mixing them into calculations. This makes it easier to test results, update the tool, and explain how it works as project needs change. Python code. Reusable script components. Create reusable components for engineering automation by separating calculation logic from file handling. Then present the results in a short, well-formatted design report. The script imports tools for working with files and temporary storage. It uses the CSV module for reading and writing CSV data, pathlib for managing file paths, and tempfile for creating a temporary directory that is cleaned up automatically. The setup defines 3 key values for voltage drop calculations: a standard voltage of 240 volts, an acceptable voltage drop limit of 3%, and resistance values for different wire types measured in ohms per 1,000 feet. Together, these values provide the basic inputs needed to estimate voltage drop for each circuit. The function creates a new cable schedule file in the chosen folder and prepares a small set of circuit data for it. The data includes a header row and entries for circuits such as panel A, motor 1, and pump 2, with each entry storing length, current, and wire type. This provides a simple dataset for later processing in the script. The code creates a CSV file by opening the target file for writing with proper line handling, then using a CSV writer to format and save all rows of data at once. After the file is written, the function returns its path, so the rest of the program can access the new file. The function opens a CSV file using the path library for cross-platform compatibility, then reads it with the CSV dictionary reader. Each row becomes a dictionary using the column headers as keys. The function returns a list of these row dictionaries, making the data easy to work with later. The function cleans the circuit and wire inputs by removing extra spaces, then converts the length value into a number, using 0 if no length is provided. This prepares the data for later validation and calculations by making the identifiers consistent and the length usable. The code First converts the row's current value into a number so it can be used in calculations. It then checks that the circuit name is present, the wire type is recognized, and both length and current are positive. If any of these checks fail, it raises an error to mark the data as invalid before further processing. This code returns a dictionary that stores key details for each circuit record, including the circuit name, wire type, wire length in feet, and current in amperes. Organizing the parsed data this way makes it easier to use in later calculations. This function estimates a circuit's round-trip voltage drop using the wire type, circuit length, and current. It looks up the wire's resistance, accounts for the full out and back length of the circuit, and converts the result to the proper units. It then compares the drop to a fixed voltage value as a percentage, which helps judge whether the drop is acceptable. The process makes a copy of the original record so the source data stays unchanged. It then adds the voltage drop, the drop as a percentage of total voltage, and a circuit status. The status is marked as passing if the percentage drop is within the allowed limit, or as needing a check if it is not. The function builds a reusable cable report as plain text. It starts with a report title and column header, then adds one formatted line for each result, showing the circuit, wire type, voltage drop, percent drop, and status. The voltage values are rounded to 2 decimal places, and the final report is returned as lines joined together with new line breaks. The code counts how many circuits need review by checking the results marked for checking. It then adds a summary line showing the total number of circuits processed and how many require review. Finally, it combines all report lines into one text string, separated by new lines. The workflow creates a temporary folder, writes a sample cable schedule file, and then loads that file as circuit records. The CSV reader turns each row into a dictionary, and each raw record is then parsed into a validated, structured form. This prepares the circuit data for the next stages of processing. The program calculates voltage drop for each parsed circuit record, adding the drop amount and percentage to the data. It then sends the results to the report function, which formats a readable summary of each circuit's voltage drop and status. Finally, the report is printed to the console for a clear overview of the analysis. This script calculates voltage drop for electrical circuits using sample cable schedule data. It reads and validates circuit length, current, and wire type, then estimates the drop from the wire resistance over the full round-trip path. Each circuit is compared with an allowed voltage drop limit and labeled as passing or needing review. The final report lists each circuit's voltage drop and status, giving a quick view of which circuits meet the design criteria. Coherent script assembly. Coherent script assembly means combining separate parts into a predictable, easy-to-follow tool. A well-built script guides data from input and validation through organization, calculation, and clear output. The main workflow should make the tool's purpose obvious, while reusable functions handle the detailed tasks. A clear script separates responsibilities. File handling should read and write data, while calculations should work independently from where the data comes from. Using suitable collections, such as lists or dictionaries, helps match the structure of the information and keeps the script easier to follow. This organization makes the tool simpler to test, update, and understand. When building a script, focus on clear control flow, useful error handling, and a smooth user experience. Check for problems, such as missing files, before later steps depend on them, and make error messages easy to understand. Well-organized output helps users make decisions, so the tool should guide the workflow and present results clearly without requiring the user to know every function behind it. Python code, coherent script assembly. Build a complete engineering workflow by keeping inputs, calculations, and reporting clearly separated. This structure makes the process easier to understand, check, and maintain, while keeping results concise and reviewable. First, import the path handling class from the pathlib module to work with file system paths across operating systems. Then, import the CSV module to read and write CSV data. Together, these tools prepare the program to manage file locations and handle CSV files. The process sets up two file locations, one for feeder input data and one for the voltage drop report. The input file contains details such as feeder length and current, while the report file stores the calculation results, keeping the source data and output clearly separated. A list is created to hold sample electrical feeder records. Each record stores the feeder name, its length in feet, and its current in amperes, with the values saved as strings. This sample data will be used later as input for the workflow. The input file is opened for clean CSV writing, then a dictionary-based CSV writer is set up using the first record's keys as column names. The header is written first, followed by all feeder records from the prepared data. This creates a structured input file, ready for the next steps in the workflow. The function first checks whether the required input file exists. If it is missing, it raises a file not found error, so the program stops before continuing with incomplete data. The code opens a CSV file and reads each row as a dictionary, using the column headers as field names. It converts those row dictionaries into a list, then returns the list so the data can be processed in a structured way. The function creates an empty collection to hold cleaned feeder records, then processes each input record one at a time. For each record, it converts the length in feet and the current in amps from text into decimal numbers, ensuring the values are ready for later calculations. The function validates each feeder record by making sure the length and current are both positive. If either value is 0 or negative, it raises an error to prevent invalid data from being processed. Valid records are added to a prepared list with the feeder name, converted length, and current, which is then returned for further use. This function estimates the voltage drop percentage for a feeder using its length, current, and a default voltage of 240 volts. It applies a fixed resistance per foot, calculates the drop over the round-trip conductor length, then converts that drop into a percentage of the total voltage. The function builds a voltage drop report by starting with a title and column header, then processing each feeder in the list. For every feeder, it calculates the voltage drop percentage from its length and current, marks the feeder as OK if the drop is 3% or less, and marks it for checking if it is higher. It then adds a formatted report line with the feeder name, drop percentage, and status, repeating this until the report is complete. The function builds a report line for each feeder by combining its name, voltage drop, and status into a clean formatted string. The name is left aligned, the voltage drop is shown to 2 decimal places, and the status notes whether it is acceptable or should be checked. Each line is added to a report list, which is returned for output or further processing. The workflow loads feeder data from a CSV file, then validates and converts each record into a usable form, checking that length and current values are positive. It then calculates the voltage drop percentage for each feeder using the appropriate formula. Finally, the results are formatted into report lines ready for output. The code saves the voltage drop calculation results to a text report for later review. It then confirms the tool completed successfully, shows how many feeder records were processed, gives the report location, and displays a short preview of the output. The code prints the report headers, then displays voltage drop details for the first and second feeders. If a problem occurs, such as a missing file or invalid data, it catches the error and reports that the tool stopped safely, along with the error details. This script demonstrates a simple engineering workflow for checking voltage drop in electrical feeders. It creates sample feeder data, reads and validates it, then calculates voltage drop from feeder length, current, and resistance per foot. The script produces a report showing whether each feeder is acceptable or needs review, saves the report, and prints a short summary to the console. It also handles common errors, such as missing files or invalid data, without crashing. Reusable report functions. Reusable report functions keep engineering scripts clear by separating calculations from how results are presented. Instead of spreading formatting throughout a command line tool, a single reporting function can turn structured data into consistent, readable output for screens, files, or reports. This makes results easier to maintain, document, and use for engineering decisions. A good report function should depend on a consistent input structure, rather than hidden calculations in the script. By organizing results before reporting, the function can focus on formatting, labels, titles, and summaries, which keeps the main script clearer and easier to test. It also lets updates, such as adding a project name or timestamp, be made in one place, improving consistency and saving time in engineering documentation. Reusable report functions make engineering workflows clearer by combining data file handling with consistent, formatted output. They can process equipment records, report successful calculations, flag problems, and explain unusual results. This helps users understand what was evaluated, what assumptions were made, and where data issues occurred, even after the script has finished running. Python code. Reusable report functions. Reusable reports help keep engineering tools easier to maintain, while structured results ensure consistent output formatting. This example focuses on summarizing voltage drops across circuit branches. The code imports two tools, one for working with file paths across different operating systems, and one for handling dates and times. These imports support tasks such as managing files, timestamping reports, and logging events. A small dataset is created to store engineering results for electrical circuits. Each rec describes one circuit, including its name, current, length, voltage drop, and voltage limit. Organizing the information this way makes it easy to manage, access, and use later for processing or reporting. The code reviews each result and compares its voltage drop with the allowed limit. It then marks the result as passing if the drop is within the limit, or as needing review if it is not. This adds a clear status to each item. The build voltage report function creates a formatted report for voltage drop data using a project name and a set of records. It first checks whether any records are available. If the list is empty, it returns a no data message instead of trying to process an empty dataset, making the function simpler and more efficient. The report is built by creating a collection of text lines that will be output one by one. It begins with a title and project name, adds a timestamp showing when the report was generated, and then includes column labels for key circuit details, such as current, length, voltage drop, limit, and status. A dashed separator is added after the header to make the report easier to read. The code goes through each record and creates one formatted report line for it. Each line includes the circuit name, current, length, voltage drop, voltage limit, and status, with spacing and decimal formatting applied for alignment. The completed line is then added to the report's list of lines. The code counts how many circuits are marked for checking because they exceed voltage drop limits. It adds that summary to the report, then joins all report lines into one neatly formatted text string ready to display or save. A voltage report is generated for the Training Lab Feeders project using the available results data. This creates a formatted text summary of voltage drops across the circuits. A save location is then set up so the report can be written to a text file on disk. The code saves the formatted voltage drop report as a text file on disk using the path library's write_text method. It uses UTF-8 encoding so characters are stored correctly, making the report available later for reference or sharing. The code displays the full voltage drop report in the console so it can be reviewed immediately. It then prints a confirmation that the report was saved, including the report file name for reference. This helps verify that the file was created successfully. This script creates a voltage drop report for electrical circuits using a small set of circuit data. It checks each circuit against its voltage drop limit and labels it as passing or needing review. The build voltage report function formats the results into a clear text report, prints it to the console, and saves it as a text file with a confirmation message. Final tool evaluation. Correctness checks. When evaluating an engineering tool, first confirm that its results are reliable. Test simple cases against manual checks, such as voltage drop, and make sure estimates for power or current follow standard engineering logic. Also verify that units, input ranges, and unusual data are handled sensibly so the tool does not produce misleading outputs. To check whether an engineering tool is correct, test more than normal inputs. Focus on edge cases such as very small, very large, missing, zero, negative, or out-of-range values where errors often appear. Use realistic scenarios like motor circuits or battery backups so the results reflect imperfect real-world data. This helps confirm the tool is reliable and robust for engineers. When assessing an engineering tool, check that it reports errors clearly and records outputs with enough context. It should warn users about problems such as missing inputs or unreadable files and explain how to fix them. Its reports should include key inputs, units, and warnings so results can be understood, shared, and verified for reliable decisions. Python code correctness checks. Before relying on engineering outputs, first check that the tools producing them are correct. Test them with known cases and boundary cases, and make sure reports stay traceable, readable, and safe. This function computes the percent voltage drop across a conductor using the current, conductor length, resistance per 1,000 feet, and source voltage. It first rejects invalid inputs such as negative current or length, or a voltage that is 0 or less. If the inputs are valid, it calculates the round-trip voltage drop, converts it to a percentage of the original voltage, and returns the result with a success message. The code first checks that the inputs make physical sense. Current and length must not be negative, and voltage must be positive. If any value fails these checks, it returns an invalid input result. This prevents the function from using unrealistic values in its calculations. The function returns no result and reports invalid input when current or length is negative, or when voltage is 0 or negative. The message reminds the user to provide physically meaningful values with non-negative current and length. To find voltage drop in a single-phase circuit, use the round-trip conductor length by doubling the physical length in feet. Convert that length to thousands of feet, then multiply it by the current in amperes and the conductor resistance per 1,000 feet. The result is the voltage drop across the conductor in volts. To express voltage drop as a percentage, multiply the voltage drop by 100, then divide by the original voltage. This shows how large the drop is compared with the starting voltage, making it easier to judge its practical significance. The function returns two pieces of information: the voltage drop as a percentage of the original voltage and a simple status message saying OK. This lets the caller get both the calculation result and confirmation that the inputs were valid in one call. The test cases cover key scenarios for a voltage drop calculator using dictionaries with inputs and expected results. They include a normal manual case that should produce about 1.667% voltage drop, a zero current case that should produce 0% drop, and a negative current case that should return no result because the input is invalid. Together, these cases check typical behavior, edge behavior, and error handling. An empty results list is created to store test outcomes. The program then goes through each test case, calculates the voltage drop, and compares it with the expected value. This process checks whether the voltage drop estimator works correctly across predefined scenarios. The voltage drop percent function is called with the test case values for current, wire length, resistance, and voltage. It returns both the calculated voltage drop percentage and a status message showing whether the inputs were valid. This keeps the calculation controlled while quickly flagging any input problems. Each test checks whether the calculated voltage drop percentage matches the expected result. If both values are missing, the input is treated as invalid and the test passes. Otherwise, the test compares the two values and passes when their difference is less than 0.01, allowing for small rounding differences. The code stores each test result by adding a compact record to the results list. Each record includes the test name, pass or fail status, voltage drop percentage, and a short status message. This makes the outcomes easy to trace and review later. The report begins with a short header to mark the start of the correctness check and keep the output organized. It then identifies the tool being evaluated as the single-phase voltage drop estimator, giving readers clear context for the results that follow. The program goes through each test result and separates its key details, including the test name, whether it passed, the calculated value, and any message. This makes it possible to report each outcome clearly without adding unnecessary detail. The results can then be formatted to show which tests passed or failed and include the most relevant supporting information. The result display shows whether the voltage drop calculation was valid. If the calculation fails because the input is invalid, it displays invalid. Otherwise, it shows the percentage rounded to 3 decimal places for a clear and consistent result. This line prints a concise summary for each test case. It shows the test name, whether it passed or failed, a voltage drop result or an invalid value, and a status message such as an error or confirmation. This makes each outcome easy to trace and understand. The code checks whether every test case passed by reviewing the pass status in each result. It then reports whether the tool is ready for engineering review, saying yes only if all tests passed and no otherwise. This gives a quick readiness summary based on the test outcomes. This script tests a voltage drop calculator using predefined cases, including a known manual result, zero current, and invalid negative current, It verifies that valid calculations match expected percentage drops within a small tolerance and rejects physically meaningless inputs. The script reports each pass or fail result, then gives an overall summary of whether the tool is ready for engineering review. Readability review. A readability review checks whether a tool is clear enough for others or your future self to understand, trust, and maintain. In electrical engineering, this matters because unclear scripts can be hard to verify even if their calculations are currently correct. Clear names, logical structure, and simple explanations make inputs, calculations, and outputs easier to follow, supporting reliability and safety. When checking readability, make sure the tool uses language that matches the engineering task. Choose meaningful domain-specific names, add comments only where decisions are not obvious, and make error messages tell users what to check. Clear wording reduces guesswork, helps prevent mistakes, and supports faster, more reliable design reviews and troubleshooting. A readable engineering script should be easy to update as tasks change. Good organization groups related ideas and avoids repeated logic, which reduces errors during modification. The report should also be clear, with labels and units that help engineers and technicians interpret the results quickly. Together, a clear script and report make the tool more reliable and useful. Python code readability review. Before relying on engineering automation, first check that its output is readable and meaningful. Names should reflect electrical engineering concepts accurately, and reports should use clear labels with appropriate units. The script starts by importing tools for path handling and JSON data. The path library helps manage file system locations in a clear, cross-platform way, while the JSON module supports reading and writing structured data. Together, these imports prepare the script for later file and data management tasks. A feeder case dictionary is created to store key information for an electrical feeder design. It identifies the feeder as panel LP2 feeder and records a system voltage of 480 volts, which is needed for electrical calculations and component compatibility. The feeder is set to carry a load current of 92.4 amperes, while the conductor is rated for up to 125 amperes. The calculated voltage drop is 2.7%, which stays below the maximum allowed limit of 3%. The code sets a report file name for the feeder case, defining where the readability review results will be saved. This ensures the report is written to a consistent, easy-to-access location for later sharing and review. Define a set of required data fields before running engineering calculations. These fields include the feeder name, system voltage in volts, and load current in amperes. Checking for them first helps prevent errors and ensures the analysis has the information needed to be accurate. The code defines the required inputs for a feeder case, including conductor rating, voltage drop limits, and the report file name. This lets the program verify that key data is available before running engineering calculations or generating reports, helping prevent missing information and related errors. First, check the feeder case for any required fields that are missing. This is done by comparing the required fields with the fields present in the feeder case dictionary and collecting any that are absent. Identifying missing data early helps ensure the case is complete before calculations begin, reducing the chance of errors later. The code verifies that the feeder case includes all required fields before any calculations continue. If something is missing, it raises an error that stops execution and identifies the fields that need to be added. The code finds the load margin by subtracting the load current from the conductor rating. This shows whether the conductor has enough capacity to carry the load safely, supporting the reliability of the electrical design. To evaluate the feeder, first check that its load margin is 0 or positive, which confirms the conductor is not overloaded. Then, compare the actual voltage drop percentage with the allowed maximum to ensure it stays within limits and supports reliable, efficient operation. The report is built by adding text lines to a list. It begins with the title, Readability Review Report, then adds the feeder name and system voltage from the feeder case information. Including the voltage with its unit makes the report clear and specific. The report formats the load current, conductor rating, and remaining current margin to one decimal place, each labeled in amperes. This makes the values consistent, easy to read, and clearly shows how much conductor capacity remains beyond the load. The code adds report lines showing the voltage drop percentage and the maximum allowed voltage drop, both rounded to one decimal place. It then checks the load margin and marks the feeder as passing if the margin is non-negative or failing if it is below 0. This gives a concise result for whether the feeder loading is acceptable. The code adds a report line that shows whether the voltage drop is within the allowed limit, marking the result as pass or fail. It also adds a review note to confirm that names, limits, and units are clearly shown, making the report easier to understand and verify. The code creates a file path from the report file name, then writes the readability review results to that file. It combines the report lines into one properly formatted text block, with each line separated by a new line. The text is saved using UTF-8 encoding, producing a small, shareable report. The process saves a structured review summary in a JSON file. It records whether the loading is acceptable, whether voltage drop is within limits, and the load margin, which is the difference between conductor rating and load current, rounded to one decimal place. This makes the results easy to audit and review later. The code saves the summary as a machine-readable JSON file. It converts the summary data to a JSON string with two-space indentation for readability, then writes it to the summary file using UTF-8 encoding so a wide range of characters is supported. The code prints a brief summary showing that the readability review is complete, identifies the report file and feeder, and reports the current margin in amperes. It then gives quick pass or fail results for two key checks: whether the loading is within acceptable limits and whether the voltage drop stays below the maximum allowed percentage. This script reviews an electrical feeder design by first confirming that all required data is present. It then calculates the remaining capacity by comparing the load current with the conductor rating, and checks whether both loading and voltage drop are within acceptable limits. The results are saved as a text report and a JSON summary, and a brief console message confirms completion with the feeder name and pass or fail status. Workflow usefulness. Workflow usefulness means an engineering tool not only gives correct results, but also fits smoothly into the engineer's normal process. A useful tool reduces manual effort, lowers the chance of errors, and presents inputs and results in a way users can easily understand. If preparing data for the tool takes more effort than doing the work manually, the tool is not yet practical for the workflow. To judge whether an engineering workflow tool is useful, evaluate how well it supports the full path from problem to decision, not just its calculations. The tool should work in realistic situations, guide users toward valid inputs, handle unusual values, and produce reports suited to different roles. Its real value comes when the output clearly supports the next step in the user's workflow. A useful engineering tool should remain reliable over time, adapt to future needs, and make repeated analyses easier without becoming fragile. Clear formats and naming conventions help users archive, share, and understand results. The best tools save time, improve consistency, preserve assumptions, and support sound technical judgment. Python code workflow. Assess the workflow's usefulness using relevant engineering examples, and compare the effort required by the tool with the effort of doing the work manually. Keep the findings concise and focused so they are suitable for a design review. The code imports Python's built-in CSV and I/O modules to prepare for working with CSV data. The CSV module supports reading and writing tabular data, while the I/O module allows text streams to be handled in memory. Together, they make it possible to process CSV content efficiently without using files stored on disk. The code stores feeder case data as a CSV-style string, with headers such as name, voltage, current, length, and voltage drop percentage. Each following line represents one feeder and its values. This makes the data easy to read, process, and use for later analysis in the workflow. The estimated manual task time is set to 24 minutes. This provides a baseline for comparing how much more efficient the workflow tool is than doing the work by hand. The tool is estimated to complete the workflow in 6 minutes. This time estimate is used to compare the tool's efficiency with doing the task manually, and to show the potential time savings. The code uses the input-output module's string I/O tool to treat CSV text as an in-memory file. This lets the CSV reader process the data without creating a file on disk, which is useful for small datasets. The code uses the CSV module's dictionary reader to turn each row of CSV data into a dictionary. The column headers become the keys, and the row values become the corresponding entries, making each field easy to access by name for further processing. First, create an empty list to hold feeder records. Each CSV row will be converted into a dictionary containing the feeder name, status, and voltage drop percentage, making the data easier to access, analyze, and report. For each CSV row, the code converts the voltage drop percentage to a number and checks whether it is 3% or lower. Feeders within that limit are marked as passing, while higher values are marked for review. Each result is stored with the feeder name and percentage, making it easy to identify which feeders need attention. The code first checks whether any records were loaded. If none are found, it raises an error to stop the workflow early. This prevents later processing from running without valid feeder data. The code counts feeder records that still need review by checking each record's status and totaling those marked for review. This gives engineers a quick count of feeders that may require additional attention. The code measures how much time a tool saves by comparing it with manual work. It subtracts the tool's completion time from the estimated manual time, giving the minutes saved and showing the efficiency gained. The workflow builds a short report that summarizes the usefulness of a voltage drop tool. It includes the number of feeder cases processed, estimated manual time, estimated tool time, and the resulting time saved. It also notes how many cases need further review, giving stakeholders a concise view of efficiency and any borderline cases that require attention. The code goes through each report line and prints it to the console. This presents the workflow usefulness check results clearly and briefly, so the user can understand them without being overwhelmed. The code finds the feeder with the largest voltage drop by using the max function to compare each feeder record by its voltage drop percentage. This highlights the most critical feeder, helping engineers focus their analysis where the voltage drop is highest. This step finds the feeder with the largest voltage drop percentage and reports it as the worst case. It identifies the feeder name and its voltage drop value, helping engineers quickly spot the most critical feeder that may need attention. The final print statement closes the workflow by highlighting the practical value of its results. It reminds the listener that the code's outputs are meant to support actionable engineering decisions and guide the next steps in the process. This script measures how much a workflow tool improves the review of voltage drop data for electrical feeders. It reads feeder data from a CSV file, flags each feeder as passing or needing review based on acceptable voltage drop limits, and summarizes the results. The report shows that the tool saves 18 minutes, identifies how many feeders need further review, lists the total processed, and highlights the worst voltage drop case for engineering decisions. In this lecture, you learned to design a command line engineering tool with clear inputs, calculations, outputs, and error behavior. Integrate functions, collections, file handling, and formatted reports into one coherent script. And evaluate the final tool for correctness, readability, and usefulness in an electrical engineering workflow. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.